do this exactly as we have it, then it's going to be, we need to find absolute value signs. I think we found these before, didn't we? Template. Okay, so go to the template again on the gray model, you've got to do control multiplication. The black model, the touchscreen, you've got a button all to itself. Down here on the second row, you've got absolute value signs. So we'll do that, and we're going to put in, what is it, x minus 3. And we're going to move outside the absolute value signs, and we've got to put in a less than or equal to. Now, on the touch screen, once again, if you look on the control of the equals, you've got all of those. However, if you're on the click pad, if you do, let's try that. I think it's control less than, yep, there it is, control less than, you get the less than or equal to. It doesn't show that, but that's what that is. Now, if you didn't know where to find that, on top of the book, the catalog, if you look at that, you've got a symbols palette. Control on the catalog is your symbols palette, so you can always go there and find it also. Okay, less than or equal to 2, tab, and we're down to the second piece. This is easier. This is 2, tab. We know how to find our template for absolute value, so we're going to put that in, and we'll finish this problem up here. And it is greater than 2. Okay. Okay, press enter when you're done. Does the graph verify what we just went over? Is it continuous? Does it appear to be continuous? Okay, now remember, appearances can be deceptive, so we have to make sure about that. But yeah, if we press enter on this, there it is. Here is our 1. Here is our 5. All we see is this portion of the cosecant. This is our 2, and this is our 2. Okay? So now we have to make sure. The only place this could break down, and this happens in life, the weakest part of something is at the joint. Okay? Same thing here. The only place this can break down now is at the joint at 1 and 5. So now we go back to our work. Is this going to break down at 1 and 5? And I'm going to erase this, and instead, while you're thinking about my question, I'm going to copy this. There we go. Okay, so there's our actual graph. What are our 3 conditions for continuity? Okay, is the function defined? Okay, that's the first thing we have to say. So is f of x defined at where? Yeah, at x equals 1 and at x equals 5. Okay, is it defined there? Well, what is f of 1? Now, which piece of the function are we allowed to look at for 1? The cosecant piece or the horizontal line piece? The only place that 1's included is up here, okay? So this would be then cosecant x times 1 divided by 6. We know that answer. We're not going to go back and do it again. The answer is 2, okay? What about f of 5? Oops. Pi times 5 divided by 6, we found that also is equal to 2. So is the function defined at 1 and 5? The answer is yes. Okay, check mark. Excuse me. Second piece is what? Yeah, does the limit as x approach that value, does the limit exist? Okay, that's the next question. So now we have to say, well, the limit as x approaches 1. Now, if x approaches 1, inherent in that statement is what? From both sides. Okay? So we better take a look at that. If as it approaches 1 from the less than 1 side, what's our limit? So we approach 1 from the less than 1 side. Which piece of the function are we using? The cosecant or the linear function? Linear function. Okay. So as we approach it from the less than 1 side, what's the limit of the outputs? 2. Okay. As we approach it from the greater than 1 side, what piece are we using? Must be the cosecant piece. Okay. What's the limit? 2. Okay. Therefore, what's the limit as x approaches 1? 2. Okay. Let's do the same thing with approaching 5 from the less than 1 side. As we approach 5 from the less than 5 side, I should say, so over here is our 5. We approach it from less than 5 side. Which piece are we going to use, the cosecant piece or the linear function piece? Cosecant, and the answer is 2? Yep, okay. And as we approach 5 from the greater than 5 side, what's our limit of the outputs? And again, it's on the linear one, so it's 2. Therefore, the limit as x approaches 5 is what? 2. Okay. Now, that's the second criteria. The third one now becomes our most important one. What is that? Absolutely. Is f of c, does that equal the limit as x approaches c? Okay, by the way, we'll put a check mark because that it happens. Okay, so f of 1, is that the same thing as the limit as x approaches 1? Yes. Okay. F of 5, is that the same thing as the limit as x approaches 5? Yes, they're both 2's, right? We got it. Is it continuous? Yeah, absolutely. Now, when we look at the graph of that, again, we have to be careful because looks can be deceiving. The only way we could actually talk about this graphically would be to put a point on. So if I put a point on here, and I change that value, let's say, to 1, does it allow me to place a point there? Remember, if it doesn't allow it, it's going to come up and say you can't use that input. It gives you an error message, and we have to kind of fudge it a little bit, but it absolutely allows us to put it there. If we do another point on here, and we put a point, let's say, over here, and I do the very same thing, I'm going to change the coordinates of that to be what? 5. Will it go there? Absolutely. So the points do exist. I can start over on the left side, and I can trace this completely and never lift my pen once. Okay, so we can use that pencil definition now to back it up. Okay, that is probably one of the more involved problems. It took me 3 pages here to do that, and how much time did we spend? Okay, so it took a little bit of time. Actually, we did a little review as we went through this because I knew you probably needed a little review on some of these, like absolute value and the unit circle, unwrapping it, and so forth. But we are basically, you know, you've got to take your time with these. And if you're not, if you're not taking your time and writing all this information down, how much of this should you write down? You know, almost all of it. You know. And so when you do a problem of this nature, you probably ought to reserve a whole page to do that. And we're not used to doing that much work for one problem. But to really show that we understand it, we have to. Okay, the next one, yeah.
So the point of the problem is to find the removable discontinuities.
Oh yes, did we answer the question?
Not quite.
Not quite,
The
okay.
graph is continuous, so there are no removable discontinuities.
Okay, yeah, we found that it is continuous at those points, so the conclusion is, therefore, it is continuous where?
That's it.
So we say it's continuous. Yeah, got to put our conclusion down. I almost forgot where I was doing. Therefore, f of x is continuous where? Where? The only places it could possibly break down are at the joints. Did it break down? Is cosecant continuous between 1 and 5? Yeah. Is the horizontal line continuous everywhere? So the entire function, both pieces included, is continuous everywhere. Okay, there are no discontinuities. Okay, thank you for reminding me to go back and make our conclusion. Any other questions on that? Okay, the next problem, again, I think we've talked about this. I think it came up in some of the Chapter 1 material, but let's go over it again, because, and we don't use this a whole lot, so if you kind of forget it, it's, it happens, and I just want you to be able to see it occasionally. We don't use this function very much in this course, at least. Greatest integer function. The greatest integer function of a number, so the greatest integer, if I were to just give you some examples, the greatest integer of 2.3 is the greatest integer that does not exceed 2.3, and that would be 2. Okay? The greatest integer, so we're going for integer. Okay. This becomes a little tricky in our minds. What if I gave you the greatest integer of negative 2.3? Yeah, be careful. This greatest integer that does not exceed negative 2.3. I heard negative 1. Yeah, it's negative 3. Remember, negative 3 is less than negative 2, so we'd have to make sure that we put negative 3 down. So those negatives can kind of trip us up a little bit. Now, I know that you know what limits are, and you know how to go about doing this problem. This would be very difficult to do with the tools we have right now with analytical. So we're just going to go to our graphical way, and I just want to share with you what we do graphically with this. Okay, let's go to our inspires. And I'm just going to go in and pick up another page, so we'll have F2 of X. Now the greatest integer function, different calculators use different abbreviations for it, and this is one that I had to kind of hunt and peck for a little bit. So I'm going to check about